All right, Calculus 12. How's it going? It's Mr. McPhee here. Having a good day. My neighbor was out cutting the lawn today, and I'm just waving at them out the window. They've just gone by a minute ago. Here I am doing math, and they think I'm crazy just talking to myself. That's okay. All right, here we go. Today's lesson is Newton's method, which is the one section that we didn't do out of the chapters 3 and 4 before the break. So this is 3.6. Practice would be 1 to 8. Now, I'm not a big fan of just the practicing of Newton's method. What I think Newton's method is really good for, though, is the development of where it comes from is really, really, really important, I think, for you future engineers and scientists, because the thinking behind the logic of its method is more important than the actual usage of it in itself, because it could lead to future things that people haven't invented yet, or things in math that people might not know. So I think it's the theory behind this that's more important than the actual execution of the actual process, which I think you'll see in a minute, because the execution of the process could be done in 10 seconds with Desmos. It's what's happening behind the scenes that's the important part. So here we go. So the theory is, and you'll see why you really don't need Newton's method, there's other methods that could be doing this, is it's used to find roots or zeros or x-intercepts for, say, complicated functions that can't be solved algebraically very well. So if you were given, let's say, a function f of x, you'd be asked to find out its roots or zeros or x-intercepts. Now with Desmos, if I had the function, I could just go and type it in and then click on the x-intercept, done, it's over, okay? But in the old days, before they had technology, this was a way that they actually could find a very complicated answer to a question that would be very hard to graph. But like I said, for us in our day and age, we could have another way out, but it's the process or the thinking behind Newton's method I think is the important part. So our goal today is to find the roots or the zeros or the x-intercepts of an equation that's either equaling to 0 or representing a x-intercept. So the theory behind Newton's method is, the graph here is just for a visual. You don't need the graph when you're doing the picture, but it just helps to think about it. Is Newton said, you know what? If we can pick an answer that is close-ish to the root, it can even be far away, but as long as it's somewhere near the root, and if we go up to the graph and develop the tangent line equation, Newton's thinking, although I don't know if Newton really is to credit for this, his name's on this, but I don't think he actually came up with it. But that I'd have to look into. His theory was, pick a root or an answer that's close to the root, go up to the graph, find the tangent line. The x-intercept of that tangent line would be a better approximation to the root. So then they would call this would be x2. That was the first guess. This tangent line led to a better guess, and then you keep going. So then you pull that up to the graph, do another tangent line, and then you get even closer to the root. And you keep doing that over and over and over until you're happy with how many decimal places that are not changing. Okay, so so the theory behind this, that's the neat part to me of that thinking of that actually does get closer and closer and closer. And in the old days, they had lots of time. They would just kind of iterate and iterate and iterate over and over and over again until they got really accurate decimal places, even up to like 10 decimal places without calculators, which is pretty amazing. So the theory behind this is this. So here's the development of the formula. How are we gonna make something do this? And it's very computer-like, very iterative. So first guess leads to the second guess, leads to the third guess, and so on and so on and so on. So the theory behind it is this. If we look at this first tangent line, and we know how to build tangent lines really quickly. Tangent line equations we know are built with that formula, or mx plus b, it's up to you, but I'm going to use this for convenience. This point here, that would be the x1, y1, and the y value, y1, another way of writing y1 would be f of x1, which just means the value of the function at x1. So instead of y1, f of x1, same difference. And the slope, we know the slope with calculus at x1, another way of saying it, is the derivative at x1. So that's the tangent line for any function. To find out its x-intercept, what do we know about this point? We know that that is when that line crosses the x-axis. That's when its y is 0. So if you make this y value 0, we can solve this equation for x. So number of ways we can do this. I can divide by, I'm going to divide by the derivative of x1 on both sides and end up with this. Just be careful with notation, and that would equal x minus x1. And then I'm one step away for solving for x. I can just add x1 to the other side. So I end up with this general formula, so to speak. Now remember what that gives me. That gives me the next x value, which we're going to call, that's going to be called x2. So that's my next answer. So my first guess was x1. That all led to x2. And then what are you going to do with x2? Well, you're going to do the exact same thing with x2 that'll lead to x3. So it just kind of keeps repeating over and over and over and over like a bad dream. So what they came up with out of this, if we know that x2 equals x1 minus f of x1 divided by f prime of x1, x3 will end up being x2 minus f of x2 over f prime of x2 for the same reasonings. And then even better, x of n plus 1 becomes x of n minus x of n, f of x of n divided by f prime of xn. And that is your kind of your formula, almost like a sequence. Well, it is a sequence, literally. And the theory behind that is, and this is where it links to other units in a neat way, as you do this over and over and over and over and over again, the limit as n approaches infinity, if you did this forever and ever and ever, x1 to x2 to x3 to x4, forever and ever and ever, this would eventually become the exact root. So that's the general formula for Newton's method of where it comes from. The thinking behind this to have that kind of logic is actually quite brilliant. That's the most important part of this lesson personally, is where it comes from. Now the usage of it, which we're going to go through 2 examples, and the examples are just really, they're really iterated. Like the process is not bad as long as you know this formula. All right, so here's the first example. First example is find the third approximation to the root of the equation x cubed minus 2x minus 5 equals 0. Start with x1 equals 2. Now, without the approximation part, if they just wanted me to solve this, I would graph that with Desmos, click my x-intercepts, be done. But now we're going to use Newton's method. So, and now how do I know to use Newton's method? It says approximation. Now, not a local approximation. This is not a Math Girl Close Enough is Good Enough video that we looked at. This is this is an approximation that's going to get closer and closer and closer and better and better. All right, so that screams, especially with this here, that screams Newton's method. Oops, Newton's method. So what I would personally do, I would write out this little formula that we came up with. It's just a matter of not memorizing it wrong. And personally for me, like I don't memorize that. Like if I really had to, I would develop it from scratch, which takes some thinking, but at least I'm not wasting memory space on this. But for you, by all means, write that down, tattoo it to your heart, but you rarely use it. You only use it if your prof ever asks you to do this university. So you pull that out, say, okay, I'm going to use Newton's method. And you might look at that and go, well, I'm not happy with that because it kind of scares me a little bit. Well, you could just write out x2 equals x1 minus f of x1 divided by the derivative of x1, and then x3 would equal x2, and just write out that if you don't like the n and n plus 1. and so on and so forth for x to x4, x5, and so on. So to use this, you obviously need a number of things. You need to look at what your original is. Remember, this works only when your function equals 0. This equals 0. So the function must be this x cubed minus 2x minus 5. If they played tricks on us here and moved the 5 to the other side, you would have to then be wise to move the 5 over and make it equal to 0 to have Newton's set up. So there's my function. The derivative, or sorry, the function is this. Hence, the derivative, which I do need, is easy. There's your power rule, 3x squared minus 2. And the only other thing you need for the formula, you just need the function, you need its derivative, and then you need the starting. And they told us that. They told us to start with the original guess of x equals 2, which would be like the equivalent of, okay, start at 2 and see what starts coming out to get closer. So there's all the data that you need. So watch what happens when I plug it into this here. So this would turn into x1. Oh, it's 2. This is going to be f of 2 divided by f prime of 2. And that will turn into, sorry, I ran out of some room here, so, excuse me, end up with 2 minus, what's the function at 2? You literally go and plug 2 into the function, divided by 2 into the derivative, and the derivative is this mess. Now I should have, I think I already did that in here somewhere. Give me a second so you don't have to watch me type it out. Oh, maybe you do have to watch me type it out. Okay, so 2 take away 2 cubed. Let me put brackets around here to be safe. 2 cubed minus 2 times 2. And I don't have to use all these brackets, I'm just getting carried away. Divided by bracket 3 times 2 squared minus 2. And my next answer out, my second closer to the real answer, is 2.1. Then what you do is you take that 2.1 and it becomes the new number that you use as your next iteration. So now you go over to your third iteration and you'll replace this with 2.1, 2.1, 2.1. So it'll look no different than the last step, just with a new value that's coming out. So whatever 2.1 minus this mess is. So evaluate the whole thing again. Now the trouble with this though is the next iteration is going to give me an ugly number. Now again, I can cheat with my calculator a little bit and go in and replace all of these 2's, but I have to insert 0.1's. Insert 0.1. Insert 0.1. I just didn't feel like typing it all out again. Insert 0.1. I think I'll get everything. There we go. And your next iteration is 2.0945682121. And then just keep going over and over and over again. But thank goodness they only asked for the third approximation. So the third approximation is done. We had the first. There's the second. There's the third. Third approximation. 2.0945682121. Now remember, before they had calculators, they would have had to evaluate this without a calculator, which they could have done. It's just a lot of it's just a lot of multiplying, adding, subtracting, dividing. It's doable. Just our calculator makes it easier. Now, the weird thing about me, for me, is if I'm going to use this piece of technology anyway, why wouldn't I just go graph it and find it that way? So it's kind of a weird process to me. I probably wouldn't use Newton's method in real life, so to speak, but this concept of where it comes from could have huge applications somewhere in the science world that someone hasn't used yet, and if you hadn't seen it, you might not know to even think about it. So it just adds a little bit extra thinking. One last example that you will see with Newton's method would be a question like this, where they might say, use Newton's method to find the 6th root of 2 correct to 8 decimal places. Now remember, this is not local approximation, this is not Math Girl. This is meaning we want to get this answer really close without using, obviously I could just go into here and just be done with it. That's the irony of this. And just go in and do the 6th root of 2. Done. But that's not the point. I want to get to that answer with 8 decimals of accuracy without the 6th root button. So to use Newton's method, we need to think about a function that will be giving, that will equal 0, such that the roots to it are this. So you have to think about what equation would have the 6th root of 2 as its root. And if you think about it for a minute, that must be x to the 6th minus 2 equals 0. Because if you solve that algebraically, you'd subtract the or you'd add the 2 over, take the 6th root. So we know this equation is going to have this answer. Okay, now for me as a mathematician, I'd even stop there. Done. There's my answer. But we want to find it in decimal form, so now I have to go and use Newton's method. So I have everything I need. I have the function, which is this. I need its derivative, which is going to be 6x to the 5th. The only thing that I really need to start with is I just need an initial guess. Now sometimes they tell you where to guess. Here they didn't give me any point. Now if I have nothing to do, I might just take a wild guess that doesn't even make sense. But I kind of know the 6th root of 2 is between 1 and 2. So I might take my first guess as 1. Try it with 100. It's just going to take longer to get to 8 decimal places because you're going to be so far away. Okay? So I go to my formula for Newton's method, which is this guy here. Oops, make sure you write it down right. I have to think about this because this is where I would mess up. Finding my second answer out, it's going to be this. It's not derivative there, sorry. So the second answer out would be 1, because that's my initial one, minus the function at 1, which would be 1 to the 6th minus 2, divided by the derivative at 1, which would be 6 times 1 to the 5th. Now I'll show you something really slick on this machine. What I do, and again it's cheating because if I had this anyway, why wouldn't I just solve it with another method? But I just want to use technology to its advantage. What I do is I go like this. I go 1 stored as x. So right now x is now 1. So I type this formula in. Instead of putting 1, I put x. So x minus bracket x to the 6th minus 2 all divided by 6 times x to the 5th. And when I press enter, the calculator is going to plug 1 in there for me. But here's where it's even better. I will have to then record this answer. Well, let's do it this way. I'll record that answer. I then have to go and now make this value my x again, which I could do. I could actually just go 1.1666666666666, which is what it is, store it as x, bring up that formula again, and there's my next answer. But even better, watch this. So first of all, 1 stored as x, there it is. Bring this up. I'm going to add to the end of this, store it as x. So this answer is then going to pump out the answer. It's going to put it back into x. And my first iteration out, we'll write this down, is 1.16 repeat. The next iteration out would be me plugging 1.16 into all of these. But if I press enter again, the calculator is going to reevaluate this with the new x plugged in. And this would give me 1.126443678, and I can keep going till the cows come home. There's my 4th iteration, 5th, 6th, and as soon as you start seeing decimals aren't changing, you know you've done just as good as the calculator itself. So there's my final. I'll write down the 4th iteration was 1.126443678. 2497067 x the fifth 1.122492051 x the sixth iteration 1.1224. Where are we? Shoot. Oh man, okay. 122497067. There should be a 6 here. 122462051. Sorry, my eyes are going cross-eyed. 2462048, and at that point I've got 8 decimal places of accuracy. All right. So something to think about would be, does Newton's method always work, or are there perils to this? That's something you can kind of think about. There's some questions in the textbook that make you think about that, where it actually can get worse than better. But I'll leave it at that. Video has been long enough. Okay, so there's Newton's method. Have fun. Put the fun in function. Talk to you later.